Yeah, so we've done the first part. All right, so let's go over exactly what we mean by impedance. So impedance is just generalized resistance. And it shows that we have a way of basically, and it's on the next slide, we have Ohm's law, but we want to have a way of talking about all circuits, AC and DC. So we came up with this thing called impedance. And I'm going to go back over all this stuff, but this is just like gonzo physics. We go to the answer, and then I'll go back and fill in the blanks. So it's expressed in what's called polar coordinates, or a complex number. And there's a real part and an imaginary part. And we use R for the real part, which is unfortunate, but it's the real resistance. And then there's a thing called reactance. And there's all kinds of great reasons to use imaginary numbers. When you first learn about square root of -1, it's like, who the hell cares, right? But if you get into advanced math, it's very useful, and if you're into engineering. But what it boils down to is that Z is now kind of a vector. And so these two guys are vector components, the real part and the reactive part. So we have to add them as vectors. So, and they're at right angles to each other, so they're components. So it's easy. We just use the Pythagorean theorem at the end of the day. And I'm going to loop back over this and explain it in more detail. And of course, you may remember the units of capacitance are farads, and the units of inductance are henries. Some other person is immortalized. And it's the first thing people do. As soon as they come up with some new equation, they put their name on it. Although not these guys from the far past, like Faraday, Farads, were just put on there because people wanted to honor him. He was a very humble guy. I saw this really not exactly heartbreaking, but Michael Faraday was an old guy at some point, and there was this hotshot theorist here in the United States when American science was just starting to become on the rise in the early 1800s. And this guy, I can't remember his name, but he was publishing things about Faraday's work. And Faraday, you would have expected to be like Mr. Big Cheese, but he wrote this really amazing note about, could he please try and explain his theories to this humble experimentalist. I was stunned. And I've been to see Faraday's lab in London, and I've seen where he used to lecture. It's pretty amazing to they rebuilt the lecture hall, but they put everything back exactly in the same place. So I could stand in the same place that Faraday used to give his Christmas lectures in the late 1700s. It was pretty amazing. At the Royal Society in London. I had a job interview there. Anyways, yeah, see, Dr. H is hot shit. Don't tell anybody. The University College of London. It was what a trip, man. You could throw a rock at Big Ben from there, and but they only wanted to pay me $50,000 a year or something like that, and the rents in London are like 1.5 times the rents in LA. I was like, how the hell do you expect me to live on this kind of money? Unbelievable. Well, we got people applying. Well, they wanted me, but I told them no. Anyways, yeah, let's get into it. So as I said, it's just, Z is just a replacement for R. So we've seen it before. The Z of a resistor is just R. The Z of a capacitor is the chi term, and it's minus 1 over 2 pi times F times the capacitance. The minus sign is important. And for an inductor, and I forgot to put the chi L here, equals 2 pi times F times L. Notice it's not inverted. And if you think about it, that makes complete sense, because, and this is hint hint what you need to explain your graphs. The resistance of an inductor goes up with frequency. The resistance of a capacitor goes down with frequency, because frequency is in the denominator. Now, rules of combination. Well, series, you have 3 impedances in a row, and so you just add them, Z1 plus Z2 plus Z3. And at the moment, we're going to ignore the vector part of it, because we're just going to say, what if there are 3 resistors? Well, that one was pretty easy. And then what about inductors? Well, that's not too much harder. So 2 Z total, L total, that's an L down here, is equal to 2 pi F times L total. And I can write out each one of these, 2 pi F times L1, 2 pi F times L2. But of course, 2 pi F is a common term, so I can pull it out. And lo and behold, it's you just simply adding them, just like resistors. And now you're saying, but yo, H, remember when we added capacitors in series, we had to do this invert shit. And it's like, uh-oh, look at this. Well, what's the total capacitance? The Z of a total capacitance is 1 over 2 pi F times C total, isn't it? Just because there it is. And I do a similar arrangement as I did for the inductor. And look at that. We end up with the rule of combination for a capacitor, even though we started out with this equation up here. So there's no contradictions. So far. Okay, so well, of course, nobody asked me to go back to. Everybody finished with slide 11. Nobody yelled at me. Okay, then there's slide 12. I'd like to go to slide 13. I'll just see if anybody says, whoa, 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 go back. There you go. I knew so. Oh, 11. Okay, yeah, there we go. No worries. I'm happy to do it. Welcome. And well, it's being recorded in Zoom, and I'm making a local recording that I can post up pretty quickly. Don't forget my YouTube channel, right? Every time I make some video, and every lab, I make a playlist for it. And some of them I already have playlists. Okay, so then that's our series combination. And now the parallel combination is pretty much the same as resistors. And once again, though, the fun part is when we get down to capacitors, and we end up with the rule of just adding them together instead of using the inverses. Now, in this slide, notice the only part that's different than the previous slide is the stuff below rules of combination. This is all the same up here. So get this down, and when you get down, if you want me to, ask me if you'd like me to go through the steps for well, any of them. The inductor, I think, should be straightforward. The capacitance might be a little confusing. So if you like, I can make a clean sheet and do the capacitor derivation if anybody would like me to. Jack's still snoozing out back there. I should turn the Jack cam back on. Okay. It's okay. Excuse me. Drank my Gatorade too fast. It's okay if I go on to the next slide. Okay. Looks like it. Well, you just yell if you want me to go back. Okay. So now we have stuff you've already have seen on previous slides. There's the list of the different impedances, and then now this is new here, this polar axis. It's just sort of X and Y. There's nothing fancy about it. So we have the real part, which is generally the resistor, and then there's the imaginary axis, but you can just think of it as the chi axis. So this is now, if we want to add together a mixed circuit. How do we do a mixed circuit? See, I was hard at work this morning getting ready. I even used lots of colors. I want to get a Microsoft Surface, so when I go back in the classroom, I can... You know what I do now is, depending on what the classroom looks like, I project my slides onto the whiteboard, and then I write on the whiteboard. But then that's difficult to save those. In principle, they have cameras in every classroom, but I haven't really been able to get a meeting of minds with the people who support those cameras. Oh, Jack is stirring. Okay, so the next slide is basically, it's just a duplicate with some extra stuff on it, so don't panic. So the first thing you do is you find out what is your chi total. Because we can't simply add r's and chi's, but we can add the chi's together. And I've drawn it here, and the orange is the chi inductor, the pinkish color is the chi capacitor, And in this particular case, we're just going to assume that the chi for the inductor is bigger. It's not always true, and it changes with frequencies too. It doesn't have to do exactly with the value of the inductor or the value of the capacitance. So I add the two of them together, and that's, now the minus sign becomes apparent, becomes important. And two vectors along a line, you can add them together as long as you remember the signs. So this is what's something about, it's beyond physics 1200, but the chi L and the chi C point in opposite directions. But this is also why resonance happens, but I will table that one for the time being, and I'll explain that later or next week. So first you determine the total chi, and you draw it here. Well, you don't have to draw it, but this is what's going on behind the scenes. So I have a resultant in green, the chi total. So the orange is chi L, the pinkish is chi C, and the green is chi total. So the only thing now, I've put the R vector on there. R goes along the R axis, and that's this sky blue. Looks more like turquoise to me, but they call it sky blue. The axes look like sky blue to me. And so then what you do is you find the resultant of adding together chi total and R. And this is the right triangle, and this is where the Pythagorean theorem comes in. I'm hoping, yeah, you guys, I'm pretty sure, I think we went over this. You guys have seen vectors, right, and vector components. Making notes to myself here. Week 14, inductors, tuner, and then real RLC tests, measurements. Yeah, in fact, I know exactly how we'll do it too. Yep. And, of course, the magnitude of it are these three steps here. The real part squared, the resistor squared, plus the chi total squared, which is chi L plus chi C, which we had written down a little while ago. And then at the end of the day, that's the 2 pi F times L minus, don't forget, 1 over 2 pi F C squared. And that is our total impedance. And, of course, since we have vector components and we have a resultant, there is an angle of that resultant, but that's not critical, and we're not going to even consider that in Physics 1200, so don't stress about it. But it has to do with what happens is, excuse me, as that angle grows, and in just FYI, that angle is called a power factor. And so if I have a factory and then it has electricity coming into it, so it's not as important for houses, because houses, for the most part, you don't have too many motors. And even though, and you don't run them that often, you don't vacuum 24 hours a day or run your washing machine 24 hours a day. Excuse me. But in a factory, of course, you do. And motors have inductance and they have capacitance. And when they're all connected together, the amount of the total capacitance and total inductance changes over time. I mean, it's all 60 hertz, but depending on how fast they're going and such, those things can change. Now, if theta is the ideal situation, is when chi L and chi C equal each other, and then theta equals 0, and that means that the power company, all they do is measure how much current passes through your meter. They don't really have a way to measure how much potential energy has been taken out, because what happens is when theta is not equal to 0, the power goes into the inductances. It's called reactive power. And it just it's like dropping a marble inside of a cup. And it slops back and forth in there. But the thing is that it comes shooting back out again. It goes back to the power company. The power company, all they know is that the current went in and the current went out. But the reactive power is imaginary, literally. And it's not useful work. So factories, they have a gadget that measures theta all day long. And then they fight it out with the power company, or they they say, all right, well, because they don't want to pay for any electricity for when theta is not equal to 0. Because that's not being turned into useful work in their electric motors. So I mean, in principle, we could have it on our houses, and people will try to sell these things to you. But it's just not worth the trouble on a house because, again, you're not running electric motors 24/7. I mean, maybe when your air conditioner is on or your heat in the winter, but it's still lighting is what uses up all your electricity. Okay, so then let's take a look at some real application. And I was a little bit of a stinker with you guys because in this case, this is now for a series circuit. But it might be, you know what, we have to, let's see. This is the series circuit, and this was pretty straightforward. We get the same total. So now let's take a look at a voltage divider. Oh yeah, you might want to draw this. So there's no reason to write out all this stuff because it's basically the same as what we just finished doing. The series circuit. I added here in the beginning it's as vectors. We generally don't write the vector symbol because everybody knows when you do impedances you have to be careful. But just as we just went through, these are notes, the original notes, the colored ones I made today. This is leftovers from Monday, and I figured I realized I could do a better job. But we added first we add together the chi's. Then we have the R, and we just add them as vector components. So now we apply it to a real-world situation, our voltage divider, right? Because we want to see how an LC behaves together. So in this case, it's pretty straightforward because these two guys are both chi's, so we can just simply add them. And, if I square it and square root it, it's really, just so you don't get scared by this, at the end of the day, it just equals 2 pi f L minus 1 over 2 pi FC. It's just complex algebra. You're supposed to do this business here, but it's just an old habit of mine I should get away from. So remember too, from now on we're gonna use it in this form. So it's Z of the LC because that's our R2. And this is our R1. But of course R1 plus R2 is equal to is Z total. So remember that I'm just adding the same slide with some more stuff added to it. In a series circuit, and just focusing on the LC part, because V out depends on how L and C behave together. In a series circuit, the high resistor, the high Z, dominates. So we should expect in our graph at low frequency, the capacitor will have the higher Z. ZL will be low, but it doesn't matter because the high one dominates. And then at high frequency, the Z of the inductor will be high, so V out will also be high. So excuse me, I wrote ZLC here and I shouldn't have written. This is V out over V in. So at high frequency, it will also be high because now the inductor will dominate. But there should be some sweet spot where they're both equal to each other, and that's about as low as they can get. And this is the so-called resonance equation. Frequency of resonance, and I didn't write it here. Let me, gosh, that's messy looking. I'm sorry about that. F resonance equals 1 over 2 pi square root of LC. In fact, this is a point of analysis for your graph here. Calculate F res equals 1 over 2 pi square root of LC, and I bet you're going to find that the place where they cross, you can estimate it. You don't have the data for that point, but you can estimate it because remember, you know L and you know C. There, we wrote them down. And just hint, nod, nod. You see I have the LC plotted here. And in fact, another hint is when you do your LC data, make sure that one of the frequencies for your LC data that let's see, what time is it? There's an hour left. And make sure let's make sure that we include the F resonance. And I have that already there. Okay, I have a spreadsheet prepared for us in Google Drive. Okay. So we're almost done. So let's see about a parallel RLC. So we know that V out over V in is going to equal R STD, R DUT. So it's going to equal to the R DUT divided by the R total, or the Z, excuse me. So let's see. Well, look, we have two in parallel. So to do remember first we do the chi's. And in this case, they're in parallel. Give me a minute. Yeah. 1 over Z total equals 1 over ZL plus 1 over ZC. Oh, chi. Keep forgetting that. Let's see. Chi L equals 2 pi FL chi L C equals minus 1 over 2 pi FC. So it's 1 over 2 pi FL minus 2 pi FC. Okay, so that's implied. So at the end of the day, the chi total is equal to 1 over, let's see, I got it here, I'm going to be lazy. Yeah. I mean, it gets pretty messy. So it's not exactly the same as it was before. But the thing to notice is because it's in the inverse of before, it's in parallel. So that means that the lower Z dominates. So if we do another look at frequency and the V out over V in, at low frequency, the inductor has, oops, that's the inductor, has a low chi. So V out over V in is going to be low. And at high frequency, the capacitor has a low impedance. So also, this is going to be low, because our DUT will be low. And then at that sweet spot, it's actually the opposite behavior as the series circuit, and it's still, though, the same equation. And this is how one makes a radio tuner. And we can go into that. And I showed you the spectrum graph here. Let's see. I still got it running? Yeah, here it is. And this is, oh, this is with the tuner. So I have a tuner circuit here, so it's picking out this one frequency. If I turn on the raw frequency, the raw antenna, so now we see the several radio stations. And we'll get into this more next week. And now with the tuner circuit, it's killed the other guys, killed the 60 hertz noise on the left, and I see mostly just this one station up here. But we'll look at that next week. Alright, so I have to get the spreadsheet ready. So while I'm doing that, make sure you have your Tinkercad circuit set up. And I'd like to take this series data. So I'm gonna on my other screen here, I'm going to get the spreadsheet set up. Unless, does anybody need to see that slide some more? Well, okay, I just 6 of one, half a dozen of the other, huh? Okay. Boy, I tell you what, I'm tired. Okay.